Now the question becomes, notice in this case I took the limit as x approached a value, and I got a plus or minus infinity. Now the question that I'm interested in is what happens if I take the limit as x approaches plus or minus infinity of f of x, and I get a number, like the limit as x approached infinity of 1 over x. I got 0. What does that imply? Well, think about that. If I have a function, oops, and I'm going to go to positive infinity, all right, and let's call this L. So this is going to be y equals L. As x gets closer and closer to infinity, f of x gets closer and closer to L. Well, how can that happen? Well, I can have it happen like that. I can have it happen like this. Heck, I can even have it happen like this. I can have it flex back and forth. An example of that would be, for example, if I took, let's kick over here. I'll leave it in green because it's pretty. If I take the limit as x goes to positive infinity of sine x over x, well, what's going to happen to sine? Sine's going to go back and forth between 1 and -1, right? And x is just going to get huge. Well, what does that imply? This limit, this is, I don't know, let's put this parenthetically, this limit is going to be 0. Now, let's go back to this. What does this line look like? What does this line right here look like? Well, guess what? It's a horizontal asymptote. We now have a limit way of talking about horizontal asymptotes. So let's write those up. So think about it. We just defined it, vertical asymptotes using limits, and now we have this wonderful way of defining horizontal. Wow, too much caffeine at lunch, guys. It's a bad thing. Well, I guess it depends. It's a bad thing in Ripley. Sorry, horizontal asymptotes. All right, now think about that. All right, so let's just build a horizontal asymptote that we can look at. All right, so I've got my function right here, and I've got this. I'm going to call this thing y equals b. All right, if I want to redefine horizontal asymptotes in the context of limits, it's really simple. I simply say if the limit as x approaches positive or negative infinity of f of x equals b, right? Doesn't this imply that y equals b is a horizontal asymptote? Now, I'm going to show you a nasty way to do something, and then I'm going to just sort of beg for your common sense and your knowledge that you already have. I hope that you never think that I want you to abandon things that you were taught before. In some cases, we were taught things because they were simpler to teach in absence of calculus. And then I'm going to want you to use calculus because it's simpler. But in other cases, using calculus or using concepts such as limits and continuity is actually harder because you've already got good stuff on the hard drive. Calculus is meant to simplify things, to make things easier for you, make things more parsimonious, not to make things more difficult. So, I shall jump off of my high horse. Ready? Let's say that I want to take the limit as x approaches, let's go positive infinity, just to keep it simple, of x squared minus 3x plus 2 over 5 minus x squared. Now, on the face of it, it can be really tricky to say, okay, wait, I'm taking a limit at infinity. What does that imply? Well, if I want to do this strictly algebraically within the context, what I'm going to do is I'm going to multiply by this goofy looking 1. And you may say, Ripley, wait a sec, why are you doing that? If I take x goes to infinity, what's this going to turn into? I'll show you. I'm going to get 1 minus 3 over x, because that x squared and that x cancel, right? Plus 2 over x squared, all over 5 over x squared minus 1. Right? Now I know that the limit of the sum is the sum of the limits. I also know that the limit of a quotient is the quotient of limits. So I basically just plug the thing in. That's what that allows me to do. Well, as x goes to infinity, this guy goes to 0. This guy also goes to 0. And this guy also goes to 0. Right? And I get -1. That's the limit. Now you may remember, God, I hope you remember, that back in the day, in pre-calculus and in Algebra 2, what we knew is if I have a rational function, all right, if I have r of x equals p of x over q of x, right? And now let's think about this. If the degree of p, we had three different instances, the degree of p was greater than the degree of q, not theta, didn't this imply no horizontal asymptotes, right? 2. If the degree of p equals the degree of q, then y equaled the ratio of lead coefficients. Remember that? It's starting to fade. Well, that's exactly what happened. This is a lead coefficient. This is a lead coefficient. The ratio was -1. And then remember, let's go 3, if the degree of p is less than the degree of q, then I know that y equals 0 is my horizontal asymptote. Okay? So do you see what I'm saying here? I don't want you to abandon that. Now, let's explain why this guy is true within the context of limits, or within the context of limits at infinity. If I take the limit as x goes to, let's go positive infinity, well, let's go negative infinity, who cares? And I'm going to get 3x plus 2 over x squared minus x minus 2. All right? Now look really closely. What we have here is a tug of war in a fraction between the top and the bottom. As x gets negative huge numbers, well, what happens to the bottom? This thing gets really big, right? As x gets huge here, right, this thing's going to get big, but it's not going to get big as fast. It's actually getting big in the negative direction, but I'm going to imply that it gets huge. That's what this means. Because this guy, really this guy, gets bigger so much faster out at infinity. Really out at infinity, this goes away and this goes away. So this whole thing can sort of be distilled to 3x over x squared. And out at infinity, what this turns into is 3 over x, right? And this goes to 0. And if the degree of the denominator is greater than the degree of the numerator, that's always going to happen. It's going to win the tug of war. And if your denominator gets bigger faster in a fraction, then guess what? Your fraction goes to 0. If your numerator, let me change colors here real quick. If your numerator gets bigger faster, then it blows up and goes to infinity. Now, let's go back. Let's say that I want to do, let's go back and take another limit at infinity. Let's say that I want to take the limit as x goes to negative infinity of e to the x. Now, there's lots of ways to deal with this. I could do it numerically. I could plug increasingly large negative numbers into x, into my calculator, and see what happens. But you know me. I'm way more a fan of the graphical / visual than I am of the numerical. This is y equals e to the x. As x gets huge negative, what does e to the x get closer and closer and closer to? 0. What does this imply? Y equals 0 is a horizontal asymptote. You see that? Now, this is not a rational function. I don't have the ability to talk about degrees of top and bottom, numerator and denominator. I have to think about this in a far more intuitive way by looking at the graph. Or, like I said, think about it. If I plug in e to the negative huge, right? I know this isn't mathematically sound, but work with me. All right? Doesn't this become 1 over e to the huge? Well, 1 over e to the huge numbers are huge to begin with, and you raise those as exponents of e, and you can see that this thing goes to 0. So guess what? We now have a fantastic way to define asymptotes. I mean, take, for example, remember arctan. Remember y equals arctan of x? I think this is in your book. I'm not sure. I don't remember. Arctan of x. Remember that guy? It looked like this, and this was the inverse of tangent, and we had those horizontal asymptotes. These aren't so horizontal. Bear with me, would you please? Y equals pi halves, right? Well, now I know, because of looking at the graph, I know that the limit as x approaches infinity of arctan of x is equal to pi halves. I also know that the limit as x approaches negative infinity of arctan of x is negative pi halves. So there's this kind of one-to-one correspondence between what we know about the graph and what we can now say about the limit. We can use the limit as a tool to tell us what the graph is doing, and we can use the graph as the tool to tell us what the limit is doing. All right, I hope that was helpful, you guys. We're going to play a lot more in class, and just we'll enjoy it, and we'll talk to you soon. All right, have a good day.